Hi guys, welcome to this solution paper on the GCE Chemistry Paper 2 by Fastpapers. I hope you guys had a good exam. I hope you guys have good preparation. I know your exams are coming up. So this was a quick solution paper on the paper itself. Hopefully it wasn't too difficult or too easy, and maybe it was somewhere down the middle. And we're gonna solve this. We're gonna have a good time. And yeah, let's just dive right into it. So the first question, this is very common in all GCE papers. They're going to give you a list of compounds and they're going to ask you to find out which description matches the best with which compound. So let's begin with our first one. So our first question is asking which compound is methanoic acid. So if we're looking at methanoic acid, it is basically CHCOO. This is basically what methanoic acid looks like. Very unimpressive. So if you take a look at one of these that looks like that, so I kind of drew it a bit wrong. I think it'll be better if you visualize it like this. 1 second. So if you visualize it sort of like this, where you've got your H over here, you got your C, your O over here, and then your OH. So if you write that down, it sort of looks like HCOOH. So which one of these corresponds to that? It's compound B. So very simple. You write down compound B over here. Not to be confused with compound V. Shout out to any the boys watchers. The next one is manufactured by the hydration of ethene. So if you hydrate ethene, ethene looks something like this: C C H H H and H. So when you hydrate ethene, you're adding H2O to it. So what you're going to end up with is C, 1H, 2H, 3H, and then you're going to end up with CH, H, this will remain the same, and then add OH over here. So you're going to end up with compound C, which is ethanol. So we're going to write down compound C over here. Compound C. It's not necessary that you have to write compound. You could just get away with writing the letters. I'm just writing it for sake of the paper. So we're looking at for something that has an empirical formula of C2H4O. So you're looking for something that when you simplify it, it comes down to C2H4O. So let's see what we can immediately get rid of. So this has 1C, so this is automatically out. This has 1C automatically out. This seems like a good candidate. So we've got 2 carbons. Let's see how many hydrogens we have. We have 6 hydrogens and 1 oxygen. So this is also automatically out. Let's take a look at this one. 1, 2, 3, automatically out because 3 is an odd number. 3 is a prime number, actually. Compound E. All right, this looks interesting. We've got 4 carbons and we've got 8 hydrogens. So this empirical formula is just going to be CH2. So this is also out. Compound F. 1, 2, 3, 4. Looking promising, but there's no oxygen. So there's no oxygen. Can't keep that in. This also doesn't have oxygen. So by the process of elimination, it's going to be compound H. But just to make sure, let's check. 1, 2, 3, 4. We got C4. Hydrogen, we've got 3 plus 2, 5. 5 plus 2, 7. 7 plus 2, 8. We've got H8. And for oxygen, we've got O2. So if you simplify that, you're going to get C2, H4, and O. So compound H is your answer for this. All right, so we're looking for something that is used to make an addition polymer. So we're looking for double bonds. We're looking for unsaturated organic compounds. And of course, there's only one on the list, which is compound G. Now we're looking for an ester. So we're looking for that ester bond. So the ester bond, if we take a look at our compounds, there's only one of them that seems to have it, which which is this COO. It's going to be compound D. So the other ones have COOH, COOH. So that's the carboxyl bond. So make sure to not get your ester bond and carboxyl bond confused during the exam. So this will be a very nice and simple. State which two compounds are structural isomers of one another. So we're looking for compounds that have sort of the same formula. So same molecular formula. So if we take a look at our options, sort of a bit cluttery over here, but let's take a look at, for example, compound E. So we know that this one is C4H8. Let's take a look at compound F. This has 5 and 5, so we can get rid of F. What about G? G has 3, 2, so that's 5, and then 8, and it's also got 4 carbon. So this is also C4H8. And because they've got the same molecular, not the same molecular formula, but because they got the same numbers of carbon and hydrogen, we can say that they're both structural isomers of each other. They're just arranged differently. And so this will be E and G, and that's a very easy 6 marks that we've got. All right, so let's move on to question number 2. So let's take a look at question 2, which says iron is extracted in the blast furnace by the reduction of iron 3 oxide, Fe2O3. This process is made up of 3 steps. In step 1, carbon burns in air to produce carbon dioxide. Give one other reason why carbon is burned in air in the blast furnace. So we all know why we use coal, for example. Coal produces a lot of heat, right? So to have this reaction happen, you need a lot of energy, energy in the form of heat. Carbon is a great source of heat once you combust it, and so you need it because it produces heat. Very nice, very simple. In step 2, carbon monoxide is produced by the reaction of carbon dioxide with carbon. State one adverse effect of carbon monoxide on health. So you could write a lot of things about how carbon monoxide binds irreversibly to hemoglobin in the red blood cells, but let's keep it very simple and just say it is toxic. As long as you write that, you're good to go. You don't need to worry about anything else. So let's move on to the next question. Iron 3 oxide is reduced by carbon monoxide. So write the symbol equation for this reaction. So again, we're going to take this step by step. First of all, we're going to do iron 3 oxide. So because it's iron 3 oxide, you're going to need 2 iron, because iron 3 means it has a charge of +3, and oxygen has a charge of -2. So you need 2 of this and 3 of this. So Fe2O3 plus, let's leave some space in case we want to balance it, gives us Fe, because there's no other F, well, no, let's keep that there, and CO2. So let's go about balancing it. So we've got 4 oxygen here and only 2 oxygen here. So let's just put a nice simple, maybe before that, let's take a look at iron. So we've got 2 iron here. So we put 2 over here. So now we've still got the thing of balancing our oxygen. So because we've got 4 oxygen here and only 2 over here, what I want to do is make this, maybe I want to keep it that way. Fe2O3, we got carbon, but our oxygen isn't balancing that way. So what if I turn this, so we got 2 over here and we got 4 over here. What if I put a 3 over here? So that says, let's put a 3 over here. So 3 twos are 6. So 6 oxygen on this side, 3 oxygen here, and 3 there, 6. So this is balanced. So that's the final reaction. Most of you probably already knew this, so if you did, great. If you didn't, well, now you know. Explain why calcium carbonate is added to the blast furnace. Include any relevant reactions or equations in your answer. So when you're adding calcium carbonate, you're not adding it just because of the carbonate, you're adding it because you want to get calcium oxide. Because what calcium oxide does is it binds with silicon dioxide, which is an impurity. So as long as you remember this concept that you're trying to get calcium oxide, the rest of this answer becomes easy. So what you're first going to write is CaCO3. Obviously, you guys are going to write calcium carbonate. Decomposes to calcium oxide. And you're going to give the equation. So this equation is going to look something like CaCO3 turns into, I'm going to remove this. There we go. So now we can go back here. CaCO3 turns into calcium oxide plus CO2. Because remember, you need to include any relevant reactions or equations. And then you write down CaO combines with impurities such as sand, which is silicon dioxide, silicon V IV oxide, IV oxide. So that's basically its oxidation state, which is why you need, so this is -2, you need 2 of this, so this will be +4. And then you write down the equation, CaO plus SiO2 gives you calcium silicate. All right, so let's move on. State 2 other properties that are typical of transition elements, but not of group 1 metals. So the first one that I think of is obviously variable oxidation states. So anytime you look at transition metals, let's take, for example, iron. So you've got iron 2 and you've got iron 3. So these are 2 variable oxidation states, right? So this is something that group 1 metals, or actually no other group has, a variable oxidation state. And another thing that these transition metals have over group 1 metals is that they produce colored compounds, which are very pleasant to the eye whenever they form. So you write these. You can also write other stuff. For example, you can say that they're more dense. So I'll use a different color for that. So let's say you can write more dense. You can also say that they, what do you call it, are not as reactive. Some of you might think, okay, what if I talk about how they're not as soft? You can write that. So you can write that they're harder. You can also write, let's say, they act as catalysts, which group 1 metals can't do. So there's a lot of options. You just need to write any 2 that you want. A very popular question. If you've been doing question papers, you'll have seen this question pop up a lot of times. Explain 2 different ways in which zinc prevents rusting. So iron is prevented from rusting by galvanizing with zinc. So here's the thing. You need to mention 2 different ways. So obviously the one that you can talk about is zinc prevents, what do you call it, oxygen from reaching the surface of iron, and it also prevents water from reaching the surface of iron. And the other thing is that zinc corrodes in preference to iron. So what does that mean? So because zinc is more reactive than iron, whenever you get oxygen comes in contact with the two, it will always prefer to react with zinc over iron. So what you're first going to write is zinc forms a layer on top of iron, on top of iron. And because it's more reactive, it is able to react with oxygen and H2O, preventing them from reacting with iron. From reacting with So the main points that you have to mention is that zinc forms a barrier, or maybe instead of layer, we should write barrier. I feel like barrier is a better word. So barrier on top of iron, and because it's more reactive, it prevents oxygen and water from reacting with iron. And you can also mention that zinc corrodes in preference to iron, but not totally necessary. All right, so the next one. The equation shows the reaction of iron with steam in a closed container. So 3 iron plus 4 H2O gives you iron oxide, I'm pretty sure, and hydrogen. Predict and explain what happens to the position of equilibrium when the pressure is increased. The temperature remains the same. So whenever you raise the pressure, which way will equilibrium shift? It'll shift. So when pressure is increased, shifts to the side with shifts to side with 1 second, guys. Sorry about that, something came up. Anyways, shifts to the side with less gas molecules. So if we take a look at this over here, we're not gonna look at this because these are solids, so obviously these don't count. So for now, we're just gonna scribble this out. We have 4 moles of water over here and 4 moles of hydrogen over here. So because they're the same on both sides, there's going to be no effect on equilibrium because they're equal number. So equilibrium is only affected if one side has fewer gas molecules than the other, because that's the direction that equilibrium will shift on. So you're going to write no change or no effect, whichever one you want. And as for your explanation, you're going to write very simply that there's equal number of moles on both sides. On both sides. All right, very nice. So this question says, iron 3 oxide reacts with concentrated hydrochloric acid. The products are iron 3 chloride, and a liquid that turns blue cobalt chloride paper pink. So what could that be? What turns a liquid that turns blue cobalt chloride paper pink? So obviously that's water, right? Any liquid that turns cobalt chloride paper pink is going to be water. So if we write down, we're going to balance it in a bit. So first let's write down our reactants. So it's Fe3O4 plus HCl, keep some space for balancing reasons later, FeCl2 plus, they say iron 3 chloride. So this is going to be FeCl3 plus H2O. All right, so let's get about to balancing this. So the first thing that I'm noticing is a bit off is our number of iron. So we have 3 over here, but we have 2 over here. So we're gonna have to put an additional iron somewhere over here. Before we get to that, let's get to our oxygen because I feel like that's one of the most important things. So oxygen is not gonna be around anywhere here. So because oxygen is not over here, the only place where you can change it is going to be here. So we're going to put a 4 here, and let's see where that goes. So now we have 8 hydrogen on this side. And the only place we can get hydrogen over here is going to be over here. So we're going to put 8 over there. And so we've got 8 chlorine. So far we've got 2 on this side and 3. So we've got 5. So we really can't go above 3 iron over here without making the equation larger than needs to be. So what if we put a 2 over here? So you got 2 threes are 6, 6 plus 2, that's 8 chlorine, 8 chlorine. Let's check our iron. We've got 1 iron, 1, 2, 2 iron, so that's 3. Let's check our hydrogen. 8 hydrogen here. 4 twos are 8 hydrogen there. Let's check our oxygen. 4 oxygen, 4 oxygen. So the final equation is going to be Fe3O4 plus 8HCl gives us FeCl2 plus 2FeCl3 plus 4H2O. That's done with question number 2. So let's move on to question number 3. So this seems to be a question on enthalpies. We can take a look at table 3.1. But before that, we get like a very basic question. Describe the observation when ethene gas is bubbled through aqueous bromine. So because we have a double bond, we know that whenever you pass an unsaturated, let's say, hydrocarbon through aqueous bromine, it gets decolorized. So in the same vein, we're going to say that the aqueous bromine goes from, so remember, you're describing the observation. So you're going to write down what you're seeing. So you're going to say that you see it go from orange to colorless. So over here, you can write color changes from orange to colorless. So that's one mark, very easy. Show by calculation that the enthalpy change of the reaction between ethene and bromine is minus 107 kilojoules per mole. So enthalpy change is calculated by, so del H is equal to energy in minus energy out. So let's take a look at what our energy in is. Energy in is, you're going to break a carbon-carbon double bond. So we're going to write down the bonds over here. So you're breaking a carbon-carbon double bond, and you're also breaking a bromine-bromine bond. So if we consult the table, we see that it comes to around, this will be 610 plus 193. So your total energy that you have to give in to break the bonds is 803. So basically energy in is the amount of energy you're giving to break the bonds. So here we're breaking the carbon-carbon double bond, and we're also breaking the bromine bond, because if you take a look at this over here, this, this, and this are the same. The only thing that's breaking is this and this. On the contrary, energy out is the energy produced when you're forming new bonds. So the two new bonds that are forming are the carbon-bromine over here and the carbon-bromine over here. So energy out is going to be, we also have a carbon-carbon single bond forming. So there's 3 new bonds actually. So this is 1, this is 2, and this is 3. Because remember, you're going from a single, you're breaking the double bond and you're forming a single bond instead. So it goes from something like this to just these two together, and then you get the single bond. So it's a 3-step reaction. You can think of it that way. That makes it easier to understand why because you're not just breaking one bond over here, you're breaking these 2 bonds and you're forming a new bond entirely. So there's 3 new bonds being made. So energy out will be, energy out is the new carbon-carbon bond plus the carbon-bromine times 2, which comes to around 350, and so that's going to be 350 plus, it's 280, I think. Yeah, 280 plus 280. So let me input that into my calculator. find my calculator. Got my calculator. So if we input that, then that comes to around 910. So our energy in is 803 and our energy out is 910. So if you do 803 minus 910, we show that the enthalpy is actually minus 107 kilojoules per mole. And then finish it off by writing down shown. And there you go. So that's how you calculate bond breaking over here. Complete the reaction pathway diagram in figure 3.2 for the reaction between ethene and bromine. Label the reactants, product, enthalpy change of reaction, and activation energy. So very fun question, very easy as well, but also very easy to lose marks in this. So what you're going to do is you're going to start by placing the reactants somewhere here. It's going to be a straight line over here. Give yourself some space. Then you're going to draw the energy bump. So this is sort of the activation energy that you need. And once the reaction happens, remember, it's an exothermic reaction. So you're going to end up with less energy than where you started. So it's going to be here, and then you're going to taper off over here. So now so this should be straight. I'm just not doing a very good job at drawing it, so just kindly ignore me there. So remember that the del H is your energy change. Del H is energy change. So your del H is not going to be this entire thing. Your del H is just going to be here. You're going to draw an arrow over here and give it a del H over here. Because your energy went from, say, for example, this is 10 and this is 5. So your energy went from 10 to 5. That is your del H. Your activation energy is how much energy you needed to have the reaction get to completion. So let's say this is 10 and this is 15. So to get from 10 to 15, this was the activation energy. So we're going to highlight that by writing EA. I'm going to get rid of the numbers over here because those aren't real. And then you're going to write reactants over here, reactant, and you're going to finish off with products over here. Very simple, very easy to get marks, as long as you remember that del H is just the energy change and that your activation energy is energy needed for the reaction to happen. Energy from start to peak. I feel like that's a good way to remember. As long as you remember that is the energy you need to get from start to the peak of the reaction, you'll be fine. All right, draw a Don-Cross diagram to show the electronic configuration in a molecule of ethene. So ethene is C2H4, and you've got a carbon-carbon double bond. So we're going to begin by drawing one carbon, another one, this will be another carbon. So here's the benefit of being able to do this online. You get to show this with different colors. So we're going to have two crosses for this carbon, and we're going to draw two hydrogens over here. So this will be one hydrogen, this will be another hydrogen. So same thing over here, draw one hydrogen over here, and you're going to draw another hydrogen over there. So for this one, we're going to give another cross over here, and we're going to give another cross over here. So that's this carbon's 4 electrons. And for this carbon, we're going to do blue circles. So we're going to do a blue circle here, a blue circle here, a blue circle here. So that's all of that carbon's electrons done. So now for this hydrogen, I'm going to use green. For this hydrogen, I'm going to use yellow. For that hydrogen, I'm going to use a lighter shade. I'm going to use brown, for example. So this will be a cross. And for this one, we'll do a lighter shade of this. So you don't have to use different colors. I'm doing it to highlight and make it easier for everyone watching at home to differentiate between the two. As long as you get the number of electrons right, you should be completely fine. So that was another relatively easy question. Hopefully you all Got that one right. So let's move on to electrolysis. All right. So I'm pretty sure this is a smaller question, so it shouldn't take too long to do. So label the cathode on the figure. So here's the interesting thing. So the way I remember cations are cations because they're spelled sort of like cat ions. These are positive. So they're positive. So because cations are positive, the cathode is responsible for attracting cations. Cathode attracts cations. So to attract cations, which are positively charged, the cathode must be negatively charged. Must be negatively charged. So as a result, this is the cathode. Even though cations are positive, your cathode is going to be negatively charged. Explain why concentrated aqueous sodium chloride conducts electricity. This is very simple. You're just going to write the ions are able to move and conduct charge. Very simple, nothing too complicated. Name the product formed at the cathode for this reaction. So name the product formed at the cathode. So because we're looking at positive ions, you know that it's attracting hydrogen ions. So as it's attracting hydrogen ions, those hydrogen ions are going to turn into hydrogen gas. So hydrogen ions turn into hydrogen gas. Or you could just write H. Chlorine is formed at the anode. Construct the ionic half equation for the reaction at the anode. So you've got your chlorine negative ions, and they're going to release the extra electrons that they have. So you're going to get chlorine gas plus 2 electrons. Graphite is suitable as an electrode because it conducts electricity. State one other property of graphite that makes it suitable for use as an electrode. Very simple. Everyone should know this. Graphite is inert. It doesn't react. It doesn't react. That's why it's used. State the product formed at the cathode when molten sodium chloride is then you would write it's molten. Molten essentially means that it is liquid. So there's no H2O. As a result, molten sodium chloride, when it's electrolyzed, is going to form Na or sodium. So very easy question 4. Let's move on to question 5. So question number 5. Chlorine is in group 7 of the periodic table. The melting point of chlorine is minus 101 degrees Celsius, and the boiling point is minus 35 degrees Celsius. So explain why chlorine is a liquid at minus 50 degrees Celsius. So minus 50 degrees Celsius is greater than minus 101 degrees Celsius. So chlorine melts at minus 101 degrees Celsius. So that means that any temperature above 101 degrees Celsius and chlorine is no longer solid. No longer solid. At the same time, any temperature above minus 35 degrees Celsius and it's no longer liquid. So because minus 50 degrees Celsius is between 101 and 35, it is a liquid. So that's exactly what you're going to write, that minus 50 degrees Celsius is between the melting and boiling point plus boiling point. go. It's very simple. This is another very popular question in GCE chemistry, where they ask for the arrangement and motion of, so right now they're saying chlorine molecules at minus 50 degrees Celsius. So this is just them wanting to know if you can describe the structure and how liquids are arranged. So keeping that in mind, there's a few things that you need to write. So what you're going to write is particles are always flowing over each other, flowing over each other in close contact, in close contact with another, and then full stop. Their arrangement is random. So that's it. So 3 points, 3 marks. A sample of chlorine gas contains 1.204 into 10 to the power 20 molecules. 1 mole of chlorine gas contains 6.02 into 23 molecules. So moles is equal to mass by mR. So first we need to find out the moles. So if one, so the way you're going to do this is going to be unitary method. 6.02 into 10 to the power 23 gives you 1. So 1.204 into 10 to the power 20 gives you 1 by 6.02 into 10 to the power 23 into 1.204 into that. So this is going to give you a value of 0.0002. So now we input this there. 0.0002 is equal to mass divided by the MR. And once you do that, sorry, the MR is going to be 30. So it's chlorine gas. So because it's chlorine gas, you're going to do 35.5 into 2. And so your mass, you're going to get a nice clean 0.0142 grams. So let's move forward to this one. State the oxidation number of chlorine in CO2. So obviously in its gaseous state, it has no oxidation number, so this is going to be 0. And over here you can see 1 minus, so this is going to be -1. Very simple, very easy. During the reaction, chlorine is reduced. Explain why using ideas about electrons. So remember the acronym oil rig. Oil rig. So oxidation is loss, reduction is gain. So this is all in terms of electrons. So if you're talking about reduction, so reduction means a gain in electrons. So you're going to write that chlorine gains electrons. Electrons. Again, I apologize for my handwriting in case anyone is, I'm not exactly sure. It doesn't really translate that well online, and it's also not that good in person too. But yeah, let's move forward. Chlorine reacts with cold water to form an equilibrium mixture containing the acids HCl and HOCl. The forward reaction releases thermal energy into the surroundings. Chlorine plus water gives you HCl plus HOCl. The temperature of the equilibrium mixture is increased. State and explain what happens to the acidity of the equilibrium mixture. So your statement is going to be what happens to the acidity. So they've already said that the forward reaction releases thermal energy. So that means that the forward reaction is exothermic. So if the forward reaction is exothermic, then the backwards reaction is going to be endothermic. Oh, sorry about that. Backwards is endothermic. So because the backwards reaction is endothermic, if you're raising the temperature of equilibrium, then you're going to notice that the backward reaction is favored. So the backward reaction is favored, then you're going to get less HCl produced. So as a result, your acidity decreases. Decreases. And why? You're going to mention that backward reaction is endothermic. Because the backward reaction is endothermic, less HCl is produced. And because less HCl is produced, acidity decreases. Decreases. So HCl is the strong acid and HOCl is the weak acid. Describe the difference between a strong acid and a weak acid. So this is a tale as old as time. They've always told you that a strong acid undergoes complete dissociation to give hydrogen ions, whereas a weak acid partially dissociates to give hydrogen ions. So you're going to write that. Very simple, nothing too complicated. So you're going to write. I'm going to try and write this nicely. Strong acids dissociate completely to give H plus ions. Weak acids dissociate partially to give H plus ions. So as long as you read that, you get the 2 marks. Chloride of iron contains 34.5% iron by mass. Calculate the empirical formula of this chloride. So you're going to go the typical way. It's going to be percentage by MR. So this will be 34.5 divided by the MR of iron, which is 56, I'm pretty sure. So if you do that, you're going to get the number 0.616. Now remember, you also have chlorine. So because it's defined as just a chloride of iron, so this will just be made up of iron plus Cl. So if 34.5% is iron, then that means 100 minus 34.5 gives you 65.5. 65.5%. So this will be 65.5 divided by 35.5. And you're going to get 1.85. So once you get to this step, you're going to divide by the lowest number. So you're going to divide this by 0.616, divide this by 0.616. So this will give you 3, and this is going to give you 1. And so the empirical formula is going to be FeCl3. Very nice, very simple question. Hopefully nothing too complicated in this one. If we go back in all of it, seems pretty simple. So hopefully you guys were able to do this one. Let's move on to the next question, which is question number 6. So we move on to question number 6. Ethene is used to make ethanol and polyethylene. Figure 6.1 shows the displayed formula of ethene. Alkenes such as ethene are manufactured from hydrocarbons such as C12H26. Name this process. Whenever you're breaking down a large hydrocarbon into a smaller one, such as take for example ethene, which is C2H4. This is known as cracking. Describe the conditions used in this process. So you're going to write down high temperature or heat, whichever one you guys are more comfortable with. High temperature plus a catalyst. So these are the two things you need for this reaction. Describe and explain the effect of increasing the temperature on the rate of the forward reaction. So this is talking about increasing temperature on the rate of so this is talking about the rate. So we don't want to know whether you're going to get more product, whether you're going to get more reactant. Because it's talking about the rate, anytime you increase the temperature, so increase in temp means that your rate also increases. So why is that the case? This is because number one, you're going to write down rate increases. So why is that? This is because particles have more kinetic energy. Kinetic energy. So because they have more kinetic energy, they're able to have more successful collisions. More successful collisions. And because they have more successful collisions, the rate of reaction increases. Because at the end of the day, you're looking for more effective collisions to take place. So now we go on to position of equilibrium. So now we get to the point where we're wondering, does this shift to the right or does this shift to the left? So reading the question is very important whenever you're answering these types of questions. So position of equilibrium. So if we increase the pressure, it's always going to go to the side with less moles of increasing the pressure. So whenever we increase the pressure while keeping the temperature constant, equilibrium tends to shift to the side that has less moles of gas. So if you take a look at the reactant side, you have 1 and 2. Whereas if you look at the product side, you have 1. So if you increase the pressure, then equilibrium will shift to the right side. Shifts to the right side. So because it moves to the right side, you need to give an explanation as to why it does. So you're just going to write down very simple, very clean, that right side has fewer moles of gas. That's it. Very simple. Nothing too complicated, nothing you have to worry too much about. Ethene is used to make the polymer polyethylene. This polymer is used to make plastics. Draw the structure of polyethylene. Your structure should show 2 repeat units. So whenever you're drawing this, you always have to make sure that you're drawing at least 2 repeat units. So ethene looks something like this, and then those are your hydrogens. So you're going to break this and you're going to form a single bond. So this constitutes 1 unit. So you're going to multiply this into 2. So 1, this is 1, and then you've got 2. And then you're just going to draw the hydrogens over here. So again, this is also very simple, nothing complicated at all, nothing to be afraid of. Draw the hydrogens here, and then that. So we used to do this back then. I don't know if this is as accepted now, but I think this is good to go. Then you can draw N over here. State 2 environmental challenges caused by the disposal of polyethylene. So this one, you can get creative. So one of them obviously is more plastic ends up in the ocean, which is a big problem, obviously. And then another one is burning Polythene produces toxic gases. Produces toxic gases. Ethene reacts with hydrogen in the presence of a nickel catalyst. Explain why this is an example of an addition reaction. So whenever you have an addition reaction, so let's say you have, so what do we mean when we talk about addition? It means 1 plus 1 equals 2. So anytime you add two things together and you get one product, it's a type of addition. So you write down only one product is formed. Draw the displayed formula of the product of this reaction. So ethene reacts with hydrogen in the presence of a nickel catalyst, so you're gonna get ethane. So this, that, this, that, like this. Again, incredibly simple. You guys have nothing to worry about. And there we go. So let's move on to question number 7. As soon as large piece of zinc to dilute hydrochloric acid, the zinc is in excess. Complete the equation by adding state symbols for the products. So let's take a look at what we've got over here. Zinc combines with hydrogen chloride, and you're going to get zinc chloride plus hydrogen. So quick and easy, hydrogen gas is going to be obviously gas, and zinc chloride is soluble, and as a result, you're going to add aqueous over there. So this will be AQ. Like, what if I lower the pen size? I think that might be easier. Anyways, let's take a look. So we've got a graph over here. Let's see what the graph is showing. It shows how the volume of hydrogen changes with time as the reaction proceeds. Describe how the shape of the curve in figure 7.1 shows that the rate of reaction decreases with time. So whenever they ask whether, so since you have volume of hydrogen gas along with time, the gradient gives you the, oh, that's obviously even worse. The gradient gives you the rate of reaction. So if the gradient is decreasing, if you have a decreasing gradient, then that means that rate of reaction is decreasing. Reaction is decreasing. And if it's increasing, then it's going to be the opposite. It's going to be increasing. So as a result, you're going to write down that as the gradient is decreasing, as the gradient is decreasing, the rate of reaction is increasing. Is, sorry, decreasing. I think I spelled decreasing wrong. One sec. Decreasing. There we go. All right, so let's move on to the next question. Explain in terms of collision theory why the rate of reaction decreases with time. So as time goes, you'll notice the volume of hydrogen gas changes as the reaction proceeds. So with every reaction that happens, the particles start off very close to each other. And because they start off very close to each other, so the particles start off sort of like all close to each other. So as a result, there's more effective collisions, more collisions. However, after, let's say, a period of time, let's say after 5 minutes, the particles are farther apart. So because they're farther apart, there's less collisions. So because of this, because there's less collisions, there's less effective collisions, and because there's less effective collisions, you get a lowered rate of reaction. So you're going to write that particles move farther apart as a result. The number of collisions decreases. All right, so let's move on. The student repeats the experiment using the same mass of powdered zinc instead of large pieces of zinc. All other conditions stay the same. Describe and explain the difference in rate of reaction when powdered zinc is used. So this is very interesting. So you guys can actually do this at home. So if you have like a powdered vitamin C tablet, one of those vitamin C tablets, you can crush it up into a powder and add it to water, and you can add a whole vitamin C tablet as well. And you'll notice that the one with that's powdered tends to dissolve faster. So this is because it has a larger surface area. So because it has a larger surface area, it all comes back to collisions at the end of the day. So there's more collisions. There are more collisions. So as a result, you're going to write rate of reaction increases. Because the powder is sort of arranged all over like this. So because the powder is arranged all over like this, if you compare it, it's sort of like having a bunch of this over here. Whereas if you look at just the whole thing, it has less surface area compared to the powder. So less surface area. So that's why powdered is better because it has a large surface area and therefore you get more collisions. Excess zinc is added to 16 centimeter cube of 0.4 mole per dm cube hydrochloric acid. Calculate the volume of hydrogen gas released, measured at room temperature and pressure. So we're going to have to take a look at the reaction. So from the molar ratio is 2:1. So we're going to write that down. Molar ratio is 2:1. So let's calculate the moles of HCl. So it's going to be 16 by 1000 into 0.4, which gives you 0.0064 moles. So moles of H2 will be 0.0064 divided by 2. So that'll be that'll be HCl is to hydrogen. So that'll give you 0.0032. So now to find out the volume of hydrogen gas, very simple. All you're going to do is multiply this with 24, and you're going to get your number, which is 0.077 dm cube. All right, last few questions for this. When you add a few drops of aqueous ammonia to an aqueous solution containing zinc ions, first thing you're going to get is a white precipitate. And when you add excess ammonia, it's going to dissolve to give you a colorless solution. This is sort of lab or ATP etiquette, so not much to go about here. Give a colorless solution. Describe how to prepare pure dry crystals of zinc chloride after reacting excess zinc with dilute hydrochloric acid. So once you do all that, first of all, what you're going to do is you're going to the solution, filter the solution to get the solids. Then you're going to heat the solids to crystallization point. Heat to the crystallization point. After you're done with that, you're going to dry the crystals with filter paper. Crystals with filter paper. All right, we're almost done with the paper. So here we are at question number 8. So question number 8 is asking, propanoic acid reacts with methanol to produce an ester. Name the ester formed and draw its displayed formula. So whenever you're naming an ester, it's always going to be the alcohol first, and then it's going to be the carboxylic acid. So this will be methyl propanoate. But whenever you're drawing it, it's going to be the opposite. So if the naming convention is alcohol first and then carboxylic, the drawing is going to be carboxylic first and then the acid. So this will be C, C, and then another carbon. So this will have the ester linkage, O, and then C. So H over here, H over here, H over here, and then you just fill in the rest of that. All right, let's move forward. Propanoic acid is a weak acid. So explain how this equation is showing, explain how this equation shows that propanoic acid is an acid by referring to proton transfer. So you'll notice that a proton is essentially just a hydrogen ion. So propanoic acid is losing a hydrogen ion, H plus, to water. So you're going to mention that over there, that a proton is transferred. Proton is transferred from acid to water. So that's the first thing you're going to write. And as for weak acid, as always, weak acids do not fully dissociate. Did not fully dissociate. All right, propanoic acid reacts with magnesium. Name 2 products of this reaction. So if we do the equation, CH3CH, 2COOH plus magnesium. So we're going to call this magnesium propanoate. So I'm going to write this down over here. Magnesium propanoate. And you're going to lose, you're going to release hydrogen gas as a byproduct. So your product is going to be magnesium propanoate, and your other product is going to be hydrogen gas. So let me just finish in the reaction over there. So to completely balance this, you're going to have to put 2 over here, because to release hydrogen gas, it has to lose two protons. So two protons, so this overall charge is -2, and this overall charge is +2. So this will be, we're going to give a third bracket, CH3, CH2, COO, 2Mg plus hydrogen. Oh, and this will be aqueous. And yeah, I think that was the paper. So hopefully you guys were able to learn something. If there's any confusion, if I made any mistakes, I'm gonna say sorry in advance. Hopefully this was informative. Hopefully you guys were able to learn something. If you have any questions, do feel free to reach out. If you have any problems regarding any other topics, um, Fast Paper is always here to help you guys out. So be sure to let us know if you have any problems, any issues. We're here for you 100% of the time. And yeah, thanks for watching the video and best of luck for your exams.